ماشي.
हेलो 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 चेक हेलो
हेलो।
हेलो लो हेलो करके निकाल
Welcome to the National Center for Astrophysics, the NCI, the part of Tata Institute of Fundamental Research, functioning under the Department of Atomic Energy, Government of India. Friends, as you know, that India has been celebrating the 75 years of independence, and various programs across the country are organized as part of Azadi Ka Amrit Mahotsav. And we are also equally celebrating this Azadi Ka Amrit Mahotsav, but differently. National Center for Astrophysics is operating two facilities. One is Giant Material Radio Telescope, which is 80 kilometers away from Pune, which is the world's most sensitive and in its kind the largest facility in the world. Secondly, the very longest radio telescope in low frequency is located in Tamil Nadu called Ooty Radio Telescope. Both these facilities are operated under the guidance, instructions, and the scientists sitting at National Center for Astrophysics. We have been doing a lot of science popularization work across India, but at geometry for last 20 years plus, mostly focusing to rural area of Maharashtra to ensure that our students going to schools, colleges, even those who are farmers and various streams, they are aware what is happening at geometry. At the same time, we also wanted everybody to carry a scientific temperament, scientific attitude, and understand what is happening in and around us scientifically. Definitely, by welcoming and what is the objective of these programs, we said that now we are in Pune city, we are doing a lot of outreach work for various institutions here, but we decided to call colleges in the first place, which are located, situated around the NCI. Call them here, talk with them that what we are doing here through our students who are pursuing PhD programs here like you, and various other objectives that NCI is in mind. So, to talk about this objective is more, but the intention and what is our goals for future things, I request Professor Divya to come forward and say a few words. Thank you very much.
Thank you, Dr. Solanki, and my warm welcome to all of you, principals and all faculty members and all students. So thank you so much for joining us here today. And like Dr. Solanki said, we've been doing outreach. A lot of it has been close to GMRT, which is about 80 kilometers north of here. But we wanted to take this opportunity to invite a few of our neighboring colleges over to our campus and talk to them. Like, we had a few different things in mind as we were planning this exercise. One very important aspect of that was that when we read about science in newspapers, articles, online, most of what we come across is done in the Western world. We wanted to change that narrative a little bit to share with you that right here in Pune, and not so far from Pune, we have the world's most sensitive radio telescope. We have some of the best researchers and scientists anywhere in the world on this campus. And we are at the cutting edge of research in many different areas right here. And we are just one of the premier astronomy institutes in the country. There are many others. So right here in this country, there are many of us who are pushing the frontier of this science, just as much as anywhere else happening in Europe or US or Israel. We're just not that well set up to talk about what we do. We don't have a department set up to make pretty pictures and share with the press. But for our neighbors, we wanted them to know that here we are and we do fantastic work. Please come and listen to us. The other thing which I wanted to share, I believe all of you are computer science students, right? First year, second year, perhaps third year as well. A large part of the progress which has happened in the last decade or a bit more in astronomy is tied very closely to the developments in computer science and DSP, digital signal processing. Right? lot of problems which were simply inaccessible because the computing load they demanded was simply unaffordable, they have now become accessible. All the new technology telescopes which are being planned, they rely on the Moore's law, making this computation affordable to them and accessible to them. Right? The telescope I'm using today, it happens to be in Western Australia, produces 1 terabyte of data an hour. The next upgrade of this telescope is going to produce 16 terabytes an hour. And naturally, we rely on extremely fast computing, very parallelized and efficient algorithms to make all of this happen. So even for those of you who are not directly interested in astronomy, as a computer science application, astronomy offers some of the most challenging problems you have. And especially with AI and ML becoming more important, astronomy is one of the largest data sets, right? The billions of galaxies, which we have already cataloged. There's an even larger number of stars, which we already know about, for which we have enormous catalogs. In my own area of science, there are fantastic problems on which I'm already working with other companies, exploring artificial intelligence and machine learning approaches. That's another part of the message we wanted to share with you. The third part, I think, is that we live in a society where access to information is extremely easy, but discerning if that information is reliable or not is not that easy. So what we would like, what we would implore you to do is that no matter what you choose to do in life, do that with a scientific purpose. Be your own judge, evaluate what you hear, what you read, what you see. If it makes sense to you, go ahead, believe it. There are so many vested interests around us that it is hard to just take anything and take it at face value. So be on the lookout for evaluating whatever is it that you come across. So that scientific temper we would like you to carry with you everywhere. And the last thing which I wanted to add here is that when you look at a picture of Earth taken from the space, you just see one globe. You don't see boundaries of countries, you don't see colors of skins of people, you don't see languages, cultures, none of that. And similarly, when you look at the sky standing from the ground, all these boundaries disappear. Right? We are all under the same sky. So in that sense, the sky is also a unifying force for us. It is the same problem which we are trying to study, it is the same nature which we are trying to understand, no matter where I live on this planet or what language I speak. So that is one more thing which I wanted to sort of share with you. That is one of the things which brought me to astronomy when I was choosing my career, and was one of the things I just wanted to mention. And with that, I thank you all for joining us here, and I pass the mic back to you.
Thank you very much for the students. मित्रांनो, बऱ्याच जणांना असं वाटतं की जे दिसतंय ते सगळं आपल्याला दिसू शकेल, आणि आजच्या टॉक मध्ये तुम्हाला जरा थोड्याशा वेगळ्या पद्धतीने अशासाठी सांगतोय की हे विश्व फक्त आपल्या डोळ्याने दिसण्यापुरतं सीमित नाही, तर त्याच्या पलीकडे आणखी खूप आहे. त्यातला एक मोठा भाग आपल्या जीएमआरटी या सेंटरमधून आपण ऑब्झर्वेशन करत असतो. आजच्या टॉक मधून तुम्हाला देण्याचा प्रयत्न एवढाच आहे की ज्या गोष्टी आपण आतापर्यंत समजत होतो त्याच्या पलीकडे काही विश्व आहे का, त्याच्या पलीकडे काही ब्रह्मांड आहे का, ते आज आपण जाणून घेण्याचा प्रयत्न करा. त्याच्यासाठी स्टुडंट्स फॅकल्टी तुम्ही फ्युचर मध्ये जेव्हा काम कराल तर तुमचा कसा उपयोग होणार आहे ह्या गोष्टीचा उलगडा करण्यासाठी त्याच्याबद्दल आणि संपूर्ण या कार्यक्रमाबद्दल आपण तुमच्या प्राचार्यांचं थोडक्यात मनोगत ऐकूया. मी गोष्टींना विनंती करतो की त्यांनी थोडक्यात आपलं मनोगत करावं. संस्थेसाठी इथं गुण व्यक्त करतो की आपल्या नावाला दोनदा संधी दिलेली आणि सुरुवात आपल्यापासून झाली आणि शेवट आपल्यापासून करतो. सरांनी आता सांगितलं की आता ही जी सगळी फॅकल्टी कॉम्प्युटर सायन्सची मुलं आहे, परवाची सायन्सची मुलं होती, तुम्हाला अजून एक ऑपॉर्च्युनिटी डाटा सायन्स सेंटर सुद्धा तुम्हाला बघायला मिळणार आहे. स्टीफन हॉकिंगचं तुम्ही नाव ऐकलं असेल, ज्यांनी विश्वाचं कार्य खूप सोप्या पद्धतीने लोकांपर्यंत पोहोचवलंय. अजून ह्या विश्वात काय आहे मला वाटतं तुम्हाला पण शोधायला मिळू शकेल. अशा अनेक गोष्टी आहेत की ते शोधायचं. ही खूप मोठी संस्था या अमृत महोत्सव वर्षानिमित्त आपल्याला पाहायला मिळणार आहे. याचा पुढचं पाऊल आपल्याला कोरोनाला सुद्धा जायला मिळू शकतं. तुमचा इंटरेस्ट त्याच्यामध्ये असेल तर. आता नवीन शैक्षणिक धोरणामध्ये मल्टीडिसिप्लिनरी अप्रोच आला. त्यामुळे तुम्ही आता म्हणू शकणार नाही कॉम्प्युटरवाल्यांनी एवढंच काम करायचं का. तर म्हणलं तर कॉम्प्युटरवाल्यांना खूप क्षेत्रामध्ये काम करावं लागतं. मला त्यातली एवढी डिटेल सांगताना पण प्रोग्रामिंग करताना एखाद्या गोष्टी एज्युकेशन मधलं करावं लागतं. तिथं तुम्हाला डोमेन एक्सपर्ट घ्यावा लागतो. उद्या जर भविष्यात तुम्ही मध्ये काम करायला लागला तर हे विषय मला वाटतं तुम्हाला निश्चितपणे मार्गदर्शन करेल. एक वेगळ्या विश्वात तुम्ही आलेला आहात. वेगळे गोष्टी तुम्हाला या ठिकाणी करणार आहे. म्हणजे ज्या लहरी आहेत त्या लहरींच्या दुर्बिणींच्या जगात गॅलक्सीच्या जगात तुम्ही आता जाणार आहात. निश्चितपणे नवीन गोष्टी तुम्हाला मिळणार आहेत. ज्या तुमच्या आवडी आहेत त्या आवडी तुम्ही ह्याच्यामध्ये जोपासू शकता. खरं म्हणजे याचा उद्देशाने अष्टनावी क्लब आपल्या कॉलेजला का सुरू करू नये असं मला वाटायला लागलं की ही आपली संस्था इथं जवळ आहे. ते निश्चितपणे आपल्याला त्या पद्धतीने मदत करू शकते. हे क्लब खरं पाहिजे तर काय होतं विद्यार्थी मित्रांनो, अशा स्वरूपाचे क्लब तुम्ही चालवले पाहिजे. बऱ्याच वेळा असं वाट की कॉलेजनी कुठल्या तरी शिक्षकांनी यायचं मग हे घर सुरू करायचं. तुम्हीच विद्यार्थ्यांनी येऊन मला वाटतं तसा प्लॅन केला. अशा क्लब आपल्या कॉलेजला सुरू करावं. त्याची ऍक्टिव्हिटी तुम्हीच करावं, तुम्हीच त्याला मदत करावं. एक नवीन आपण सुरू करू शकतो. तुमच्या करून आलं पाहिजे. आम्ही अनेक गोष्टी देत असतो ते कधी कधी आपण देत असताना त्याच्याकडे पाठ फिरून जात असतात. त्यापेक्षा तुमच्याकडून जर अशी काही संकल्पना आली तर निश्चितपणे आपण राबवू शकू आणि चांगलं काहीतरी हे आझादीच्या अमृत महोत्सवानिमित्त आपण काहीतरी घडवू. आपल्याला जी संधी दिली त्याबद्दल सोळंकी सर आणि त्यांचे सगळे ओबराय सर आणि आता लेक्चर देणारे विवेक सर या सगळ्यांचं या ठिकाणी मी आभार मानतो आणि थांबतो. धन्यवाद. And without wasting too much of time, Jitendra, I hand over the stage to you. Please take everybody to your talk. Thank you very much.
Thanks. Hello. Welcome everyone. Before
They just need 1 minute to adjust. An additional window showing up on the slides.
Before I start, I want to know how many of you prefer English. Please raise your hand. And आप में से कितने लोग हिंदी प्रेफर करेंगे? Please raise your hand.
English is okay or Hindi? So you can switch on wherever you think. मराठी सगळ्यात शेवटी.
आज मैं आपको एस्ट्रोनॉमी, रेडियो एस्ट्रोनॉमी और दुनिया के सबसे बेहतरीन लो फ्रीक्वेंसी टेलीस्कोप GMRT के बारे में बताऊंगा। This telescope is developed, maintained and run by us. I'm Nitin Saral and we curated this presentation in this special occasion of Azadi Ka Amrit Mahotsav with my team Jyotirmay, Devesh and Devachatri. So, astronomy is an oldest natural sciences, from the beginning of our civilization, we remain curious about the sky and we start to taking notes of the position and the motion of the heavenly bodies like sun, moon, planets, and stars. This gives rise to a field called astronomy. The study of astronomy arouses many questions like where do we come from? How vast is our universe? Are we alone? And what is the position of Earth in universe? With the advancement of our knowledge and technology, we know a lot about our universe. But in comparison to this vastness of the universe, it looks like just the tip of an iceberg. Before we think that Earth is the center of our universe, but with missions like Apollo 11, Moon mission, we can see that Earth lies in the sky of Moon, and this image is taken from the Voyager mission while crossing the solar system. And in this image, you can see Earth as a pale blue dot. Such missions like Apollo and Voyager, there are many more missions like that, and they can put our place in this universe into perspective. Now I am going to show you a movie which shows how big our universe is and what is our place in this. So here you can see we are coming out of the Earth. As we go beyond the Earth, we can see the artificial satellite around it, like this satellite, communication satellite, military satellites, and going further beyond, we can see the moon's orbit. So here is the moon orbit, and then we can see the other planets around Earth, and going beyond our solar system. In the light of the sun, we can't see our planet at all. Going beyond, we can see the constellation, and this constellation sphere itself is a tiny part of our galaxy called Milky Way. This Milky Way is just a dust in the blue of galaxies, and these galaxies group to form the clusters, and this cluster group to form the planet. And this is the largest structure we see in the universe. And after this, we see this sphere called the CME, which is the first light of the universe. Going back, we can see how vast this scale is and what is our place in this vast universe. Astrophysics is the study of universe through the lens of physics. And the only assumption it takes is that all of physics are same everywhere. To understand this, consider me going to some place in the universe like Andromeda Galaxy or some far away. This pointer, which is in my hand, remains in my hand until and unless I throw it. Phenomena I just explained is called the Newton's first law, and it remains same everywhere. So does all the laws. From ages, astronomers observe the universe with their naked eye. In 17th century, Galileo made a refractive telescope and marked the beginning of a new era in the astronomy. But who are astronomers? Astronomers are the one who investigates the mystery of the universe. But there are limitations they can face. To understand their limitations, consider someone gives you a task of verifying the Snell's law. I hope you all know the Snell's law. It is the laws which govern the refraction of light. So I can, if someone give me that task, I can set up the verification in various ways, but I choose the easiest of all. I take the glass slab and take the laser, put the radiation on this glass slab, change the angle, and calculate the incidence angle and the refractive angles, and verify the Snell's law. But astronomers can't do the same. If someone gave them the task, what is the composition of sun? Means what is the sun made up of? Means they can't go there and do the experiment and find out the composition of sun. So there's their limitation is that they can't go to the places they study, they can't touch the things they study, they cannot do the experiment, and they can't look the object from the different vantage point. And like astronauts can't see the backside of the moon or the dark side of the moon. They can only peer out the world, the universe, through this rock we call our moon. But luckily, in 1895, the discovery of X-rays gives us the different perspective to look at the universe. For example, this is the image of an hand invisible, and on the right side, this same hand under the X-ray. And you can see these two tells the complete different story of the same object. In the X-ray, we can see the bones of the hand, but in visible light, we can only see the outer boundary of the human hand. But astronomy does not limit it to visible or X-ray. There is a whole spectrum of electromagnetic waves which we can access, from radio, microwave, infrared, visible, ultraviolet, X-ray to gamma ray. This is the image of the sun in different wavelengths. And as you can see, in the visible, we can see the photosphere of the sun. These different images shows the different layers of the sun, which we don't know without the help of multi-wavelength astronomy. This is the another example of multi-wavelength study of a galaxy, where we can see the galaxy in visible, in radio, in infrared, in ultraviolet, and in X-ray. And these different images tell the completely different story of the same object, which is the galaxy. This one shows the gases around the galaxy. This one shows the dust in the galaxy. And this one shows the starlight in the galaxy, and this one shows where the stars are born. And this one shows the center of the galaxy where black hole resides. But from the surface of Earth, even with the help of telescope, we can't access the full spectrum, because our atmosphere blocks most of it and allows only visible and radio to pass. This is both the advantage and disadvantage. The advantage in terms of that it gives life to develop. Otherwise, the rays like X-rays and gamma rays destroy all the life. Whereas disadvantage in terms of astronomy, because we can't see the universe in these spectrum, and we have to send satellites or probes or telescopes outer in this space, which are very expensive. So other than we can observe the radio from the ground, what are the special properties of observing in radio wavelength. The universe is actually has more radio light than expected. The brightest radio sources, we can't see brightest radio sources in the optical, and in the same way we can't see the brightest optical sources in the radio, because the physical process giving rise to the radio emission or the optical emission are different. There is one more advantage of using the radio, which is that the radio observation can be done both during day and night. This is the example of the sun in optical in daytime. This shows that we can't see the other sources like stars in the daytime, whereas the same image in the radio, where we can see the sun here, and we can also see the other sources like galaxies in this image. In 1932, at Bell Laboratories, Karl Jansky first detected the radio signal from space. Like many of the discoveries, this discovery is also serendipitous, because Karl Jansky himself is not an astronomer, he is an engineer, and he tried to find the source of interference in radio communication, but instead he finds a constant static hiss which repeats every 24 hours. Further so first he supposed that it must be coming from the sun, because sun actually repeats itself in 24 hours. But later he found out that the period actually was 23 hours 56 minutes. And when he discussed this phenomena with his astronomer friend, he find out that this period, he tells him that this period corresponds to a fixed star which repeat in the same which repeats itself in the same period, and this is called sidereal day. When he matched his observation with the optical catalog, he found out that this signal is coming from the center of our galaxy. Influenced Grotro River in 1937, influenced by the discovery of Carl Jansky, single-handedly built a radio telescope in his backyard and did the first detailed systematic survey of radio sky, and he found this image in 160 megahertz. But first two attempts of his are failed, where he is using the 3.3 gigahertz and 900 megahertz frequency. These initial radio telescope does not have the sensitivity and resolution to see the universe in detail. The latest achievement of human ingenuity and effort is the square kilometer array SK. Before I will go there, we have to first understand the basic of it, like what sensitivity is. So sensitivity means how faint can you see. Back in 2005, when you use a mobile camera, you can see that you can't see anything at all in the camera. But today, when you use the mobile camera, you can see faintest of the things which even your eye can't see. So today the cameras are very powerful in terms of sensitivity. And what sensitivity means to telescope means, if we understand this sensitivity in terms of radio telescope, we can see that the signals which we detect is 1,000 times weaker than a mobile phone signal. And it took about 1,000 years to even collect energy, even collect the light which the normal bulb can use in 1 second. So how can we increase the sensitivity of radio telescope? We have to develop bigger size dishes. The larger the dishes we can build, the larger the sensitivity we get. So we build the telescope like 64-meter Parkes Radio Telescope in Australia, 76-meter Jodrell Bank Telescope in UK, 100-meter Wien Bank Telescope in USA, and 100-meter Eiffelberg Radio Telescope in Germany. You can see the scale of these telescopes compared to the 2-floor buildings here. These telescopes are huge. Can we build the telescope bigger than this? If you try to build those telescopes creates engineering challenges, like the structure which support this telescope can't handle these larger telescope than this. But those engineering challenges are met, and we build this 305-meter Arecibo telescope and 500-meter aperture spherical telescope FAST in China. These uses the shape of valley, which gives them the structural support. So, what is resolution? Resolution means how much detail can you see. You may observe that while zooming is 64 megapixel image, you can see a lot more detail than zooming a 8 megapixel image. So in this example here, you can see in this right side image, there is more detail than in the left side image. So that means this image is highly resolved. So how can we achieve the resolution in radio telescope? So let's firstly compare it with the optical telescope. In optical telescope, getting the resolution of 0.1 arcsecond, we need a telescope of size 1 meter in diameter. If we want to get the 90 arcsecond resolution, we need a telescope comparable to the FAST. That means 500 meter. This is huge. If you want to get a 1 arcsecond resolution, we want a 200 kilometer size disk. This 200 kilometer size disk means, if you imagine the size of it, if we can say we live in Pune and we roam around and see and look how big the Pune is. So if we develop this disk in Pune, how much bigger its size can get. So we need the size greater than 8 times the size of the Pune. This big the area this telescope can consume. So it is impossible to build such a large disk telescope. So can we get this same resolution if we place the smaller size telescope in different places around the 200 kilometer area? Yes, a radio interferometer can do that. The concept behind the radio interferometer is that these telescopes must be in the shape of parabola, and the properties of parabola is that they can focus the light at the focus. So we can achieve the same resolution as a 200 kilometers size disk can give. So these are some of the radio interferometer around the world, like Very Large Array VLA in New Mexico, USA, Westbrook Synthesis Radio Telescope WSRT in Netherlands, Murchison Whitefield Array MWA in Australia, Low Frequency Array LOFA in Netherlands. You have seen this image all over the news recently. This is the famous M87 black hole. So this image is formed by a lot of effort by computer scientists, astronomers, and there is a huge team, like over 1 lakh people. This image you can see takes the telescope of size around 200 kilometer. If you want to see much closer than this, means we know there resides a black hole at the center. So how can we get that much resolution to see that black hole? So if you build a telescope of the size of around country, we can zoom in this region and we can see this image like this. This is the zoom in version of this area. And if we take the telescope like the size of the Russia, and we can get this much resolution. So this small portion in this image can be resolved here. So to really see the black hole, which is very small, we need a telescope of the size of the Earth, and this gives a telescope like this. This gives the image like this. So how an radio telescope forms the image, how it see it. So the general perspective is that when we see a radio telescope, so when you point a radio telescope on the sky, it will give you an image like this. But this is not true at all. The thing which actually happens is that when you point a radio telescope in the sky, those signals are weak. It receives the signal, amplify it, and then record it. Later, an astronomer analyzes those data and form this image. Radio astronomy in India started at Kodaikanal by the Indian Institute of Astrophysics (IIA) in 1950s. Jointly with Raman Research Institute, IIA operated this Gauribind Radio Observatory, which was established in 1976. The golden era of Indian radio astronomy started by Professor Govind Sarup with establishing the Kalyan Radio Telescope in 1965. These are 32 telescopes of 1.8 diameter each, and they are transferred from Sydney, Australia to India in 1958. At that time, there was a great debate going on in the cosmology that whether our universe is expanding or it is fixed. So they built the radio telescope in 1969 and find out that this radio telescope really gives the evidence that our universe is expanding. But these telescopes does not have the sensitivity and resolution to do the further observation. So we started building the much bigger telescope. So here is the construction of a telescope like this. This is a 45 meter radio telescope, and it is built in 80 kilometers north of Pune in Khodat, Naranga. There are 30 such dishes like this in a 28 kilometer of area, and they are distributed in the Y-shaped pattern. These telescopes operated at the frequency of 100 megahertz to 1450 megahertz. When this construction is finally completed, we get the world's best low frequency radio telescope, GMRT. And with this state of the art telescope in our hand, where research are we doing? Are we finding the aliens? Yes. So we are collaborated with SETI, and soon we start searching for the extraterrestrial intelligence. The other discoveries which we are making with this GMRT is the cold gas in the galaxies, the supernova remnant. The supernova remnant is basically like a star which is dead, and radio halos in the arcs and radio halos arcs and relics in the cluster of galaxies, pulsars, jet from the black holes, and galaxies which are in the very past, like when the universe first formed, those galaxies which we can see from geometry. And over the past 20 years, the geometry is all over the news. These are the major discoveries of the geometry. And with this astonishing achievement of the geometry, it will get the most prestigious award in the electrical engineering and computing. So geometry is also participating with SK, which I told you before, is the latest achievement in terms of the sensitivity and the resolution. So these are some of the pre-look of the SK when we compare it to the geometry. So the left one is the image of the geometry at 610 megahertz, and the right one is the image of the same region at 600 megahertz. And we can clearly see the major difference between these two. This one shows, this one is the high sensitive image, which can show the structures in more detail, and it is more sensitive to faint structures like this filament is very faint here in this image, but in this image you can clearly see the this filament and the more detailed, more substructure into it. That's is just a trailer. Means real picture is coming in 1929. Because Meerkat is a part of SK, which will be the SK will be operating soon. The current progress and future astronomy of India is this, that we have the world-class telescope at hand, like the GMRT at radio wavelength, AstroSat at X-rays, and UV wavelength. We have the number of good radio telescope, like the Davis-Tull optical telescope and liquid mirror telescope set up at Nainital. And we are partnering with some of the mega projects which are going around the world. Is the 30-meter telescope TMT, LIGO India, which detect gravitational waves, and square kilometer array, which is the world largest radio telescope, which is going to be the world largest radio telescope. We are also planning some space-based observatory like Aditya L1, which observe the sun, and CMB Bharat, which observe the first light of the universe, and Daksha, which is an X-ray observatory and look the sky in X-ray, and other planetary missions. So what are the career opportunities when we after you do the astronomy? So these are, you can become a research scientist, university faculty, science journalist, and science communicator. So these are some of the statistics of regarding astronomy in India. Here, the interest in astronomy is distributed according to the states, and almost all states have equal interest. But these are some of the states which come at the top. And this is the most searched astronomical related query in the internet. So how can one become an astronomer? You have to do PhD in astronomy and astrophysics. Who can apply for this? BSc and MSc, Maths and Physics student, and also the engineering student. The exam which you have to give to come into the institute like NCRA is the nationwide exam like JEST, GATE, NET, TFR, or the exam conducted by some institute like IUCAA, IISER, etc. But what are the career opportunities in astronomy for the computer science background people? So they can help us to build astronomical software. The software which we are using and which is very essential to us, means without it we can't go further, is the CASA, Common Astronomy Software Application. And this is the very important software, and this is built by the computer science. Also, we need your help in the office operation of GMRT, and also we need your help here. You can provide us technical support regarding these softwares and other things. So with that, I can stop and thank you. If you have any question, please feel free to ask.
You can raise your hands if you want to ask questions.
Excuse me. We are just waiting for questions from you. तुम्ही सर्वांनी आता ऐकलेलं आहे, त्याच्यामध्ये खास तुमच्यासाठी शेवटची स्लाइड्स पण ऍड केलेली आहे, बिकॉज मला तुमच्या फॅकल्टीने सांगितले की आज सगळे कम्प्युटर ऍप्लिकेशनचे स्टुडंट्स आहेत. हा प्रश्न एक झाला की करिअरसाठी, पण ज्या प्रमाणामध्ये आपण तुम्ही सांगितलं तुम्हाला की साईज किती छोटा असेल, खूप मोठे असायला पाहिजे तुमच्याकडनं, आपण सगळे सायन्स स्टुडंट आहोत आणि क्युरिओसिटी प्रत्येकाला असते. जर तुम्ही प्रश्नच नाही विचारले तर दोन गोष्टी होऊ शकतात, एक तर तुम्हाला सगळं समजलं नाही तर काहीच समजलं नाही का. म्हणून कोणीतरी सुरुवात करायला पाहिजे. आणि जर का समजा तुमच्या विद्यालयाच्या प्रोग्रामिंग जर का आपल्या या प्रोग्रामची सुरुवात झाली असेल आणि मला पाहिजे तुमची बॅच खूप इंटरेस्टिंग होते, खूप प्रश्न विचारले त्यांनी, मला असं वाटलं की ते मग तुमच्यापेक्षा जास्त हुशार आहेत का, असं नाही वाटलं. तुम्ही इक्वली तेवढेच हुशार, त्यामुळे ओपन टू यू. आणि आमचे सगळे यंग सायंटिस्ट तुमच्या कुठल्याही प्रश्नाचं सायंटिफिक प्रश्नाचं उत्तर द्यायला समजतात आणि कुठल्याही लँग्वेज मध्ये असू द्या, मराठी, हिंदी, इंग्लिश. फक्त त्याच्यापेक्षा बाहेरची लँग्वेज असेल तर मला तो सायंटिस्ट शोधून आणायला. येस, थँक्यू. Any questions?
So, when you collect this astronomical data, what about the storage of this data? Because further, when the research you are going to be used, so what kind of software you are using, or how it is going to be stored?
Okay, so we have the computer clusters in the GMRT to store the data, and data comes in a single operation. The data is around 50 GB of data, but with a long period of time, it will go like in TBs. And after the storage, we have to you asked about the analysis.
Yeah, like there is going to be like when periodically you are taking it is a very large amount of data.
Yes.
So you might be having your own data centers or server.
Yes.
So
So yeah, there is the data center in the GMRT itself, and when you want to when you need that data to analyze it, to see it, and
Maybe we can
Yeah.
understand a little more further.
I'll add something to what Deacon was said. So you're absolutely right, we generate a lot of data. And these data are precious for us. So what we also do is that we archive these data. Ever since the first observing cycle of GMRT, all the data which we have ever taken is available on archive, and anybody else, if they want to use it, they are welcome to use it. So naturally, to host this data, we have to have a fairly decent sized data center, right? And it's a redundant storage because you can't afford to lose these data. So we have a copy at GMRT and an identical mirrored copy right there at NCR. Each of those is also redundant. So as the telescopes grow more sensitive, the amount of data they generate increases dramatically. So not only you need to have large data storage, you need also to build systems which can support high I/O. And as it happens, this analysis is very iterative. You have to read it many times, write the data many times, read it again, and so on. So we work with sort of large scale, high performance computing systems to enable that.
Halo, apa punya orang dapat pernah jadi apa di sini boleh? Kalau orang sudah itu dia apa lagi, pakai data lagi, nggak ada yang nol. See, when you collect the data of like 50 GB from a particular source, there is some kind of interferences in that. What is called it garbage and all this thing. How do you understand and analyze that this is garbage and this is real data from the passing source?
so there are various steps in removing those garbage. Like we know that there is a limit about which a source can give the brightness. A source brightness has some limit. So above than that, that is all garbage, all are. Okay? So we remove it. So that limit we and the another thing we know there are some sources like the error chain and some sparks. Those can deviate the RFI, and those are persistent in the in frequencies and in time, and those we can when we plot the data or when we show the data, they are really apparent to us. These are the kind of sources we remove on the basis of that, and we also knew if some of our antenna is not working properly, those can use a very sometimes very low low scale data or sometimes very high scale data in terms of the flux or voltages, and those we can remove. So we can identify each and every source of that garbage individually.
Is it any scientific reason to select the product as a space for installing GMRT or just a space available? Is it a scientific reason to select that area?
Yes, there is a scientific reason. So before setting up this kind of mega project like GMRT, we travel all over the India to look for this place. The special requirement for these places like this is that there has to be low population density, because population density creates the radio noise. Like we use mobile phones, this will create radio noise. We use our bikes, scooters, and there are industries, there are shops which uses electricity, and there is a spark from it. So the area must be very far away from the human pollutions, and this is the one reason. The another reason is that it must there may be facility around that area, so that people working on the area like GMRT can easily work there, and these are the some sort of things.
I'll add something to what Nitin said. So what he said is absolutely correct. Those were the criteria we were looking at. What I wanted to add is this exercise was done in 1980s, mid 80s, right? So at that time, the landscape in terms of technology was very different from what it is now. So we were looking for a large part of flat land, not so far away from some city. And so this area is such that it is shielded from both Pune and Mumbai by some interlined mountain ranges of the Western Ghats. There was very little water and very little electricity in this area, so the prospects for development were also low. So that is what drove us to there. The other alternative site which was being considered was close to Indore. And generally people felt that this would be an access site. Things have changed dramatically since then. Now we have, power, electricity, roads, lot of infrastructure is there, population density has grown enormously, and industrial density is also growing. And that brings us to the question which you were asking about, how do you separate the garbage in your data from the acoustic? So we put in a lot of effort in identifying what is really coming from the sky and what is the contamination from some other source. But all the new telescopes which are challenging the sensitivity, the square kilometer array Nitin was talking about, they are being built in areas which have very low population density. The only areas which exist on the earth where population density are low are places which are very hard to live. So one part of that telescope is in Western Australia. It's a desert, really very little water. In summer temperature exceeds 50 degrees centigrade routinely. So apart from a few kangaroos and some emus, nobody lives there. The other part of that telescope is in South Africa. That there is again a desert there. It's a very hard terrain to live in. Absolutely no water, no agriculture, no minerals. So those are the places where we prefer to do it. But given that we have an enormous investment here at GMRT, and in India we are not going to find a place which is sparsely populated unless we go to some frozen part of Himalaya. That for other reasons is not suitable for a radio telescope. So we put in a lot of effort in trying to keep this place clean of RFI, and we have developed some of the world leading techniques in identifying radio frequency differences in our data, clean it up and use it. So despite this really high population density where we live, we still maintain the sensitivity of this telescope, right, which is really remarkable for an instrument like that.
Any question related to carriers?
Sir, how fire and smoke are getting the fire electron? How do you treat a fire? See, for any such devices, when you set up and there's a tower, nothing. If you look at the picture, just backside on the flex, that is our dish antenna and GMRT. So in the tower, there's the electronic systems, the computer system. So you normally install these smoke detectors and fire sensors. It will just sense the temperature of smoke and then give you alarm and you act on it. But it also has a cooling system, so it will provide. But yes, fire and smoke detector, like everywhere, you can find they need to be installed to identify if there is any threat.
I have a question. So, for example, there are mobile towers in areas. all us know about that mobile towers from that rays animals, people can affect. Due to these radio telescopes, is there any health issues? Because our GMRT center and all other centers in some populated areas. That's why I have a question.
Okay, so friends, these telescopes we have set up in India also. You can see the radio astronomy started in 1950. 1950 and his question is, does it affect the light, whether it's birds and all these things? See, even where there is no antennas, these rays are coming, and in one of the sides, you are seeing what kind of rays you receive on the surface of the ground. So they are not harmful. Anyway, so these rays are, we are only receiving it, it is coming, whether you have antenna or not antenna, they are coming. You are only collecting them and analyzing them. They are not harmful to the birds because harmful signals are already cut off with our natural process above Earth. But whatever is possible, that you are getting. But the man-made signals, if that is something happening, that we are not doing anything here. We are only as a receiver system, and which is naturally received to us from the cosmic sources, and the signals are very, very weak. They are not harmful for this thing. At least there is no history that the radio astronomy, while doing their observations, bird are died somewhere near antenna. Absolutely no.
Sir, what is the difference between astrology and astronomy?
So astronomy is
Okay. Astronomy, as you said, it's a science which can be studied across the globe, and you will find the same phenomena everywhere. You can find if the moon in India in this particular city rises at this particular time, you can see a variation in time because of the locations and this thing, but moon will rise everywhere in the sky of Pune, this thing is here. But when you talk about astrology, moon का effect मेरे ऊपर है क्या नहीं है, that answer from 1,000 people you will get differently. That is why there is a debate that whether it is a science or not. But astronomy is always a part which is a science, can be studied, explored, and you find all the principles exactly same everywhere if they are studied. Whereas astrology, which is the second part, which is not given at the same thing because they don't have a exact kind of explanations or theories based on that. Because of this will affect you and all these things. So nothing is there. That is why most of the astrology is not. But what we are talking about, we will give you what is the insights of known astronomical data. What is insights of planets and all these things, if in optical observation or astronomy or anything about characteristics of those objects scientifically. परिणाम क्या होना है 7.5 वगैरह, that is not part of astronomy. Still, one can learn that radio science, people debated, but that is not the topic which is learned in astronomical institute at all, or that is not there. But कधीतरी तुम्हाला असं याच्याबद्दल शंका असेल की हे खरंच कुठून आलं, you can talk some other time की 7.5 कुठून आले. People just interpret from astronomical data and then their own explanation starts, but astrology is not part of astronomy at all. You want to add something?
Like Dr. Palati was saying, that there is this positional astronomy aspect, right? Where was Saturn at the time when you were born? Those calculations one can do, we can tell you exactly the direction in the sky where every planet was there. How does it impact the life of a human being? There is no known scientific way by which the presence of any stars or sun or moon or planets can impact the life of a person. So that is beyond science. Astronomy limits itself to telling you where things are. So astrology is something which I personally don't believe in. I don't see. I'm not aware of any laws of science or any laws of physics by which a distant planet can have an impact on what happens in my life.
म्हणजे मी तुम्हाला थोडक्यात सांगतो काय होऊ शकतं सायंटिफिकली. जो ध्रुव तारा आज तुम्हाला दिसत असतो
तो 300 वर्षापूर्वीचा असतो लाईव्ह. याचा अर्थ ध्रुव ताऱ्यापासून जो प्रकाश निघालेला आहे तो आपल्यापर्यंत प्रकाशाच्या वेगाने पोहोचण्यासाठी 300 वर्ष लागतात. तसंच तुम्हाला जो काही बाकीचे जे ऑब्जेक्ट्स आहेत त्याचं सायंटिफिकली दिसतं हे सांगता येतं. आता तुम्ही जर का पंचांग मध्ये बघत असेल, पंचांग त्याच्यामध्ये पोझिशन दिलेले आहेत, कधी चंद्रोदय कधी सूर्योदय, हे तुम्ही पण ऍस्ट्रॉनॉमिकली कॅल्क्युलेट करू शकता. कारण ते जे काही ऑब्जेक्ट आहेत ते सगळ्या त्याचा फिनॉमिना कंटिन्युअसली कन्सिस्टंटली ऍज पर दी ऍस्ट्रॉनॉमिकल डेटा आहे. म्हणूनच लोक ग्रहण सुद्धा प्रेडिक्ट करतात. कारण का ह्या ज्या पोझिशन्स आहेत कोणत्या दिवशी कोणत्या वेळी कशा एक लाईन मध्ये येणार आहेत काय येणार हे ऍस्ट्रॉनॉमिकल डेटा ऑलरेडी आहे. म्हणून ग्रहणांचा अभ्यास ऍस्ट्रॉनॉमी मध्ये सुद्धा सगळे करतात, बिकॉज टू स्टडी द सायंटिफिक फिनॉमिना इन दॅट. पण त्याच्याबद्दलच्या सुपरस्टिशनच्या अंधश्रद्धा हे ऍस्ट्रॉनॉमिकल लोक बघत नाहीत, कारण त्याचा परिणाम आपल्यावरती झालाय असं करत नाही. म्हणजे आता मी तुम्हाला मगाशी बोलता बोलता म्हणले की 7.5 वर्ष कसं आहे. आता मी तुम्हाला किती वेळा माहितीये की सूर्य कोणा भोवती फिरतो का जागेवर आहे का? आपल्याला हे शिकवलं सूर्य जागेवर, पण या अवकाशातल्या ब्रह्मांडाची गोष्टी एका जागेवर नाही. सूर्य सुद्धा त्या आपल्या सगळ्यांना घेऊन त्याच्या मास्टर भोवती फिरतो कदाचित. तसंच आपले जे ग्रह आहेत ते सूर्याभोवती फिरतात. मग पृथ्वीला किती वेळ लागतो सूर्याभोवती फिरायला? 1 वर्ष. तसं शनीला किती लागतात माहितीये का तुम्हाला? शनी सुद्धा सूर्याभोवती फिरतो एक तर नक्की आहे ना, मग त्याला पण 30 वर्ष लागतात एक चक्र पूर्ण करायला. आणि आपण जे काही क्लस्टर ज्याला आपण राशी वगैरे म्हणतो त्या 360 अंशात आहे. किती आहेत राशी? 12. आणि मग कोणीतरी सांगितलं की या प्रत्येक असं भ्रमण करताना या 12 राशी जर का 360 डिग्री आहे आणि सूर्य सुद्धा 360 डिग्री फिरत असेल तर एका राशीमध्ये तो किती वर्ष असेल? 30/12, 2.5 वर्ष. मग कोणीतरी संकल्पना केली की हे अडीच आपल्या चालतात. पण कारण का मी स्टार्ट केली काहीतरी चमत्कारिक वाटतंय. म्हणून आम्ही सांगतोय की तुम्ही विज्ञानाकडे वळाल. हे सगळं काही नाही, तुम्ही म्हणाला हा हे असं असतोय मग जाऊ देत, आपल्याला काय करणार नाही. कारण त्याला स्वतःचे 63 उपग्रह आहे, त्याच्याकडे एवढे असिस्टंट आहेत. स्वतः शनी गॅस तो काही असं जमीन नाही तिथे थंड बर्फाच्या कडेच्या आतमध्ये राहतो. कशाला त्रास दिला आपल्याला तू? ह्या सगळ्या गोष्टी सायंटिफिकली विचार करा की ह्याचा परिणाम होतोय का नाही. तुम्ही ते सांगता आलं पाहिजे की तो बसलाय की तिथून प्रकाश यायलाच 1-1.5 तास लागणार आहे आपल्या समोर इथे त्याने उगवल्यानंतर तिथला बघण्यासाठी. तर त्यामुळे इतके फार बदल आहे. आणि मग अशी एका फिल्म मध्ये दाखवलं जर का आपण ब्रह्मांडात गेलो तर आपली अवस्था एवढ्या डस्ट पार्टिकल एवढी आहे की मग त्याच्यात इंडिया कुठं, मग महाराष्ट्र कुठं, मग पुणे कुठं, मग गोलक विद्यालय कुठं, मग माझा क्लास कुठं, मग मी कुठला भेटलो होतो. त्यापेक्षा आपण स्टडी करावं. आणि हे खूप चांगला सुंदर विषय की आपल्याला आलेली माहिती सायंटिफिकली अनालाइज करून आपण आपल्या बाजूला, म्हणजे जसं सांगितलं नाही कुठल्या तरी म्हणून तुम्ही तिघांना सांगा मग ते तिघांना सांगतील. सायंटिफिक प्रूफ सांगा, रुमर नको.
Sir, computer languages like Java, Python, are they required in this astronomical field?
Yes, they are required in the astronomical field. Like we generally use the Python here because it is easy. But to really write the code to do a fast calculation, to use less computing resources, we need to write it on C, C++, and yeah, they really we really use this language.
So I just want to add that what software we showed, CASA. So this is mostly written in the Fortran and the C and C++ to do all the numerical calculations and linear algebra operations. Now, when we are using the user interface, because that is you want to make that software user friendly for the astronomers. At that part, the Python and Java, this kind of languages are used to adapt the core modules of the C, C++ or Fortran, and we use the Python, Java for that. So all the different languages are used for different software developments of astronomy, and depending on what type of operations, means calculations or what type of thing you want to do with that software, depending on that we are using different kinds of software languages.
Why these antennas are connected in Y shape?
In Y shape. Okay. So basically, we are using the Fourier transform to make an image. Okay. So, do you understand Fourier transform?
So there is a very good reason for why these antennas are distributed in the shape of a Y. The mathematical reason is what you started with. I'll give you some hand-waving reason for why it should be. So imagine you are looking down at the Earth from the source which you want to study. And imagine, let's say, our GMRT is sitting at the North Pole, you are sitting at the Pole Star, Dhruv Tara, and you are looking down. Earth is rotating. So in about 8 hours, you will see that, if I call this arm A, arm B, arm C, arm A would have come to the place of B, and B would have come to the place of C, and C would have come to the place of A in 8 hours, right? Because the Earth is rotating. I have 3 arms, each of these is 120 feet apart, right? So after that, the array has become essentially the same to me as where I started from. Radio astronomy uses this idea that the array appears different to the source from where you are observing as the Earth rotates. Okay? And so, but after 8 hours, it becomes the same as what it was to start with. So to make use of this idea, we distribute the antennas in 3 arms, so that when we observe the same source for almost 8 hours, we can get the best ability to make the image of that source. You can make a larger number of arms, and then you can take less time, but then you need to make many more antennas to be able to do that. So 3 is regarded as an optimal.
I think we'll take a last question now.
Answer your question.
Yeah.
How much time it takes to collect data?
Okay, so the time varies according to the observation, and if there is a faint source, like if the source is very far away, it is faint. So we need more time because considering it like in you are taking image via the camera. So when you put the camera on the night mode, it will take a more time to take a photo. Why it will take a more time? Because at night time the sensor, the object look faint. So we need to collect the more data to form the good image out of it. So in the same way, if the object in the sky is faint, we take more time to collect the data. If it is bright like our sun, we just need only seconds to take it.
With this, we'll conclude the session here, unless one of your faculty says some you want to talk to.
Sir, what is the starting point of and this can start with? That is this good and why how to check data given a set is correct or not?
First of all, we are not collecting the data from satellite, because we are collecting from the cosmic source. Satellite data is available. Secondly, when you are using this all 30 antennas, so the resolution that you will be getting a single dish of 28 km diameter, because it is rotating. Yes, for any center, it's better resolution in here. That is why the center of this Y has 12 antennas at the sphere. If you look at that small sphere, you can point out with the pointer, that's small. So this center has 12 antennas in there, in 1 kilometer by 1 kilometer area. Remaining and 18 antennas, like 6 on each arm, they are spread over in like 14 kilometer radius, that is 28 kilometer diameter.
in radio astronomy, you are getting a reservation of single dish of 28-kilometer diameter by using some astronomical and mathematical calculations and theories.
Yeah. Yeah.
So this was very nice interactive session with the team. I would like to thank Dr. Solanki sir, head, Obrai sir, then Vivek sir, and all the student team who have done a very good interaction with our students. I would like to thank for their hospitality that they have provided in this campus to us. And in future, we will have more interactions like this from their side. Thank you so much.
With this, आपण या कार्यक्रमाची संपता करत आहोत. यानंतर